This is lesson 5.7 on roots and zeros, and also 5.8 on the rational zero theorem. So I'm going to go through 4 examples of solving each equation, stating the number and the type of roots, and then we'll talk about the last section in the chapter, which is the rational zero theorem, to finding all the zeros. So we need to factor letter A first. So that's a trinomial. That is a perfect square trinomial. So numbers that multiply to 9 that also add up to 6, and that's 3 and 3. So you might, you can write this in a couple different ways. This is like x plus 3 squared equals 0. Or you can think about that as, and I'll show you down here, this is the same as x plus 3 and an x plus 3 equals 0. So I'll show you this in 2 different ways. If you write it as the binomial squared, unsquaring something means take the square root. So this is x plus 3 equals 0. And if you subtract the 3 over, you're going to get x equals negative 3. Likewise, if you wrote it as two binomials multiplied together, if you split this apart, x plus 3 equals 0, and solve this one, x plus 3 equals 0, you're going to find that both solutions are negative 3. It just appears twice. So if you were to graph this, this is called a double root. It bounces off the x-axis at negative 3. Technically, it's a degree 2, which means there's 2 solutions, but they're the same number, x equals negative 3. So we call this a double root. I guess double real root. Okay, so x equals negative 3 appears twice, so it's a double real root. So there's 2 roots, but it's the same number. All right, letter B. It is a degree 3, so that should tell you I should get 3 zeros in the end. So if we look at x cubed plus 25x equals 0, look for a GCF first. So they both have an x. If you factor out the x, you get x squared plus 25. And now you have to set each part equal to 0. So if I set the x part equal to 0, that's one solution. And then if you set the other part equal to 0, x squared plus 25 equals 0. Let's solve for x. So let's subtract the 25. Bring it to the other side. X squared equals negative 25. Unsquare it, so square root. And like we learned previously, the square root of a negative is an imaginary number. So this is plus or minus 5i. So square root of 25 is 5. The negative underneath the radical sign is an I, and then you need plus or minus. So what do we have? This x equals 0 is one real root, and x equals plus or minus 5i. One's 5i, the other's negative 5i. So that's 2 imaginary roots. So that makes 3 zeros. So it's a degree 3. All right, 2 more. X to the 4th minus 16. So that is, first you could factor that into x squared minus 4 and x squared plus 4. It's kind of like a difference of squares. You should know that you can factor a difference of squares again. So this is x minus 2, x plus 2. You cannot factor this sum of squares though. So this just stays x squared plus 4. Now we have to set each part equal to 0 and solve. So the first part, x minus 2 equals 0. You add the 2 over, you get a solution of x equals 2. The middle section, x plus 2 equals 0. If you subtract 2, you get x equals negative 2. And then finally at the end, if you set x squared plus 4 equal to 0, you have to subtract the 4 over to the other side first, so you get x squared equals negative 4. Square root both sides. Square root of 4 is a 2, square root of a negative is an I, and then you need plus or minus. So let's reflect here. It was a degree 4, so I should have 4 answers. So these two make 2 real roots. These are real numbers. And because you have the I here, the plus or minus takes care of the other 2. So you have 2 imaginary. So 2 real and 2 imaginary. 2 plus 2 is 4. Alright, and the next one, let me get some space here. 4 terms there, so you should automatically think to yourself, grouping sounds like a good idea. So the x squared comes out of the first group, you're left with 3x minus 1. You can take out a 3 from the next group and get 3x minus 1 equals 0. Put the fronts together, x squared plus 3. Put the part that the parentheses match, 3x minus 1. And again, set each part equal to 0. So x squared plus 3 equals 0. Subtract the 3 over, so you get x squared equals negative 3. Square root. Now 3 is not a perfect square root here, but the negative underneath turns into an I in the front. The square root of 3 stays under, and we need plus or minus. So that's part of it. Then I need to set 3x minus 1 equal to 0 and solve. So add the 1 over. You get 3x equals 1. Divide both sides by a 3. So you get x as a third. If you go back up to the top, this was a degree 3. So you should have 3 roots. 1/3 is 1 real root. And the one with the I, plus or minus, is 2 imaginary roots. I'll just do imag there. So that makes 3. Alright, so that's all you need to know out of 5-7. Now 5-8. Once it switches pages for me. There we go. Alright, is the rational zero theorem. So what this means is if you have a polynomial function with integral coefficients, then every rational zero, or when the p of x is equal to 0, so when the function crosses the x-axis, is in the form of p over q, which means that's a rational number, in simplest form, where p is the factor of the constant term, and q is the factor of a leading coefficient. So I'll kind of color code this. P is a factor of the constant term. Well, if we look at this first polynomial, the constant is the number without a variable next to it. So this is P. The leading coefficient is in the front when it's in standard form. Highest exponent's in the front. Leading coefficient is a 4. So this is the Q value. So what you're going to do first is list all the factors of 16. So P16, what are some ways you can multiply to get 16? Well, that's 1 times 16. You can do 2 times an 8. Or you can do 4 times 4. So those are the factors of 16. Factors of 4 for the Q value is 1 times 4 or 2 times 2. So then when it says list all the possible values, you need to kind of think of all the possible zeros that could be an option. Now this doesn't mean that all of them are zeros, but P divided by Q. So I need to take all the factors of P and divide them by Q. So I can have 1, 2, 4, 8, and 16. If I divide them by the 1 right here, you can have plus or minus of both. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. Now if you take them each over 2, so 1 over 2, so I'm looking at that one there, so this is plus or minus a half. If I do 2 over 2, that's a 1, which I already have in my list. If I do 4 over 2, that's a 2, which is already in my list. 8 divided by 2 is 4, which is already in the list. And 16 divided by 2 is an 8, which is already in the list. Now they need to be all put over 4. So 1/4 plus or minus a fourth is a new one. 2 over 4 is a half, which we already have. 4 over 4 is a 1. We already have that. 8 over 4 is a 2. We have that. 16 over 4 is a 4. So we have that. So all the ones that I have here are possible zeros. So let's do one more. This one's a little easier. So P is going to be the 12. It's a constant term. So factors of 12 are like 1 times 12, 2 times a 6, and 3 times 4. Factors of Q, well, Q is a 1, so the only way of getting a 1 is a 1 times 1. So if you put all the possibilities of the P values over the Q values, all of those P values are divided by 1. So this is pretty easy. P divided by Q, all the possibilities are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So they could all cross the x-axis at those points. Now, when we do this last problem, it says once you have written out the possible rational zeros, you can test each number by using synthetic substitution, synthetic division that we talked about earlier in the chapter, or use other tools you've learned to determine the zeros of a function, which I'm not going to list out all the possible numbers because there's a lot of possibilities, but a good tool that we have used is graph it and look for the x-intercepts. Now you'll definitely find some that are whole numbers. You want to look for those first, and then do some synthetic substitution, synthetic division to do what we did a couple days ago in class. Then we can factor. So I already went to my calculator here. I typed in the function. I'll tell you what to look for. So if I go graph, here's what it looks like. You can't see the whole graph, but it definitely crosses the x-axis at 2. If you're not sure, you can go second graph and look at the table, and the y value is there 0 at 2. So 2 is definitely one of the roots. So I'm going to do synthetic substitution with a 2 in this box. Now check the exponents, 4, 3, 2, 1, 0, so all my coefficients. And let's do some synthetic division. So 5, 10, 2, 4, 45, 90, 18, 36. And the remainder is 0. So that's a good thing because it's one of the roots. So the remainder should be 0. So let's write this. So we drop the exponent, so now it's going to be 5x to the third plus 2x squared plus 45x plus 18. One of the factoring go-tos when you see 4 terms is grouping. So we're going to factor this by using grouping methods. What comes out of the first group? Let's see, just x squared. So then you have 5x plus 2 left over. The next group, you have a 9 that divides into both of them, so you have 5x plus 2. So the parts in parentheses match. Let's write that once, 5x plus 2. The fronts of the other ones, x squared plus 9. X squared plus 9 is not a difference of square roots, so you can't go anymore as far as the factoring goes. But we're not quite done. We have to do what we did in 5-7, so we got to set each one of these equal to 0. So we're going to subtract the 9 over. You get x squared equals negative 9, square root. X is plus or minus 3i. This one, 5x plus 2 equals 0. Subtract the 2, you get 5x equals negative 2. Divide by 5, so you get x equals negative 2/5. So this was a degree 4. Here's 2 imaginary. Here's a rational function, or a rational number. And then the third, or that's 3. We need one more, which was the one we found on the graphing calculator. So x equals 2 was the 4th one. So all my zeros are plus or minus 3i, negative 2/5, and a 2. So I'll have some questions for you to practice in Delta Math afterwards. But if you're confused or have questions, you can send me an email or let me know. All right. Toodaloo!